Welcome to today's paper reading. Today's paper is titled, Language-Quantized AutoEncoders, Towards Unsupervised Text-Image Alignment. This paper, titled Language-Quantized AutoEncoders, Towards Unsupervised Text-Image Alignment, was authored by Hao Liu, Wilson Yen, and Pieter Abbeel from the University of California, Berkeley. It is currently under review as a preprint. The key limitation of large language models is their inability to perceive visual information, which is essential for tasks involving real-world interactions such as visual question answering and robotics. To address this, we propose the Language-Quantized AutoEncoder, LQAE, a method that aligns text and image data in an unsupervised manner by leveraging pre-trained language models like BERT. This approach involves encoding images as sequences of text tokens, using BERT for reconstruction, and enabling few-shot image classification. This method allows for the use of large language models in tasks that traditionally require visual input. Figure 1 illustrates how the Language-Quantized AutoEncoder, LQAE, can be utilized for few-shot image classification by harnessing the in-context learning capabilities of large language models such as GPT-3. The process begins with LQAE encoding an image into a sequence of text tokens. Some of these tokens are then randomly masked, and the sequence is fed into a pre-trained BERT model. The decoder subsequently reconstructs the original image from the unmasked text tokens. This method allows LQAE to represent similar images with similar clusters of text tokens, thereby aligning the text and image modalities without the need for aligned text-image pairs. This alignment enables few-shot image classification, where GPT-3 can classify images based on the text tokens generated by LQAE. Figure 2 illustrates the architecture of the Language-Quantized AutoEncoder, LQAE. The process begins with encoding an image into a sequence of embeddings. These embeddings are then vector quantized using a codebook derived from RoBERTa, a pre-trained language model. Following this, a high ratio of the embeddings are masked and passed through a frozen RoBERTa model for prediction. The predicted embeddings are subsequently used by an image decoder to reconstruct the original image. This architecture allows LQAE to align images with text tokens without the need for paired text-image data, leveraging the capabilities of large language models for image tasks. Figure 3 provides visual examples of the key terminologies used in our few-shot image classification experiments. These include task induction, which is an introductory text that informs the model about the task using natural language, such as "Please answer the question." The number of ways refers to the total number of categories involved in the task, like distinguishing between dogs and cats. Number of inner shots indicates the number of unique examples of each category presented to the model, such as different images of dogs. These visual examples help clarify the concepts and their application in our experiments. Language-Quantized AutoEncoders, LQAE, are designed for unsupervised text-image alignment, with a focus on few-shot image classification tasks. Visual examples are used in experiments to illustrate the terminologies. Key concepts include the number of ways, which refers to the total number of categories, the number of inner shots, which is the number of unique examples of each category, and the number of repeats, which specifies how many times each unique example is repeated. Training details involve using the Atom optimizer with a peak learning rate of 1.5 times 10 to the power of -4 and weight decay of 0.0005, over 100 epochs with 5 warm-up epochs, a batch size of 512, and distributed training on 128 TPU v3. Figure 4 illustrates the performance of linear classifications on the ImageNet dataset, comparing the effectiveness of VQ-VAE and LQAE features. Notably, the use of RoBERTa representations extracted from conditioning on LQAE tokens significantly outperforms the VQ-VAE encoder representations. This observation suggests that despite LQAE not generating human-readable text, its learned grouping is sufficiently powerful for training a linear classifier on top of RoBERTa representations. The figure clearly shows that LQAE BERT achieves the best performance, followed by LQAE encoder combined with BERT, while the random encoder performs the worst. Table 1 presents the performance metrics of the Language-Quantized AutoEncoders, LQAE, and various baselines on the open-ended mini-ImageNet two-way tasks. The table highlights that randomly selecting between the two class labels results in a 50% accuracy rate. In comparison, the LQAE model demonstrates superior performance, achieving an average accuracy of 68.7%. This underscores the effectiveness of the LQAE in accurately classifying the images, surpassing other methods such as MAE plus linear, image pretrain plus image text fine-tune, and image text pretrain. The results indicate that the LQAE model is particularly adept at handling the nuances of image classification tasks, making it a robust choice for such applications. Table 2 presents the performance metrics of LQAE and various baselines on open-ended mini-ImageNet 5-way tasks. The table highlights that randomly selecting between two class labels would result in an accuracy of 20%. In contrast, LQAE demonstrates superior performance, achieving an accuracy of 29.04%. This indicates that LQAE significantly outperforms the baseline methods across all evaluation settings, particularly those that do not have access to text-image pairs. The results underscore LQAE's effectiveness in few-shot classification tasks, where it substantially exceeds the performance of other methods. Table 3 presents a detailed comparison of various variations of the Language-Quantized AutoEncoders, LQAE. The table evaluates the performance metrics of linear classification with BERT-like models on ImageNet and few-shot classification using GPT-3 on mini-ImageNet. Key findings include the detrimental effect of removing L2 normalization during the vector quantization step, the significant performance boost from using a pre-trained Roberta model, and the consistent improvement in results with larger GPT-3 models. These results underscore the importance of specific components and configurations in optimizing LQAE performance for both linear and few-shot classification tasks. In the related work, previous studies have shown that few-shot learning often relies on format similarity and patterns rather than the exact semantic meaning of prompts. This is evident in works by Min et al. 2022, Lampinen et al. 2022, and Websun and Pavlik 2021. Additionally, variations and ablations of the Language-Quantized AutoEncoders, LQAE, have been evaluated, particularly focusing on the importance of components like L2 normalization, the use of a pre-trained Roberta model, and the impact of entropy regularization. Furthermore, a higher masking ratio has been identified as crucial for achieving good downstream performance in tasks like ImageNet linear classification and few-shot image classification. Figure 5 illustrates the critical role of a high mask ratio in achieving optimal results with Language-Quantized AutoEncoders, LQAE. The top section of the figure presents the linear classification outcomes on the ImageNet dataset, highlighting the performance improvements associated with increased masking. The bottom section showcases the 5-way and 2-way few-shot image classification results on the mini-ImageNet dataset, further emphasizing the necessity of a high mask ratio for effective few-shot learning scenarios. This figure underscores the importance of masking strategies in enhancing the performance of LQAE across different classification tasks. The methodology in this work involves realigning representations using GPT through few-shot true text-image alignment pairs. This approach helps in solving downstream visual tasks like classification. However, the text may not always be human interpretable, which is crucial in domains like healthcare. Due to limited compute resources, scaling up the models was challenging. 2 dimensions of scaling were considered, using larger image encoders and decoders, and employing bigger BERT-like models. Both are hypothesized to significantly improve results. The method also generalizes to arbitrary modalities by training an autoencoder to map one modality to another, using pre-trained denoising models instead of BERT. This approach opens up many potential cross-modal applications across various fields. In this experimental setup, the method focuses on few-shot classification using a minimal number of text-image aligned pairs, specifically at most 5 pairs. This approach achieves classification accuracy that is competitive or exceeds that of prior works which often require pre-training on millions of pairs. Additionally, the method employs Roberta language representations for linear classification of LQAE images, demonstrating that aligning non-text modalities to text can effectively leverage the strong representation learning capabilities of BERT-like models and the powerful few-shot learning properties of these models. This approach is designed to achieve unsupervised text-image alignment, a significant advancement in the field. Figure 6 presents examples of image-to-text generation using our method, showcasing images sampled from the ImageNet dataset. On the left, a randomly sampled image from ImageNet is displayed. On the right, the corresponding text generated by the model based on the image is shown. This figure illustrates the capability of our method to translate visual content into textual descriptions, demonstrating the potential of unsupervised text-image alignment. The main results focus on the analysis of the ImageNet dataset. On the left, we have a randomly sampled image from ImageNet. On the right, we see the model-generated text based on this image. The generated text consists of a series of incoherent phrases and random words, indicating a lack of semantic structure. This highlights a significant limitation of the current model, as the generated text does not align with the image content and lacks clear context. These results suggest that the model requires further refinement to improve the coherence and relevance of the generated text. In this study, the dataset construction is based on mini-ImageNet, using a 256 by 256 image size to generate 256 tokens from the Vision Transformer (VIT) encoder. The subset of ImageNet classes, referred to as S, is selected from the validation set, aligning with previous meta-learning research. The process for generating a two-way question with n intershots involves selecting two classes, C1 and C2, choosing n images from each, and combining them into a sequence. The label is assigned based on the first class name from the ImageNet dataset. Thank you for watching.